Okay. Okay. Now let's go to chapter 2. We had some slides remaining from chapter 1, which we will go to that at the end of the class if we had time. Otherwise, I will record it for you and you could see it yourself. So let's go to chapter 2. The chapter 2 of the book. It's instructions. We have talked about computer. And then we told you that there is a hardware and there is a software. You usually write software at the top level, and the hardware at the lower level executes that. Something is in between, which we called it the interface between software and hardware. What was that? Instructions. And the vocabulary for that instructions are instruction set architecture. Instruction set, and then we will talk about instruction set architecture, how it works in a processor. Okay, so that's what we are going to talk about now. We talked about cost, performance. We talked about hierarchical layers of abstractions in both hardware and software. Then we said that the interface is instruction set architecture. And then we talked about the performance as execution time for the CPU time, and also a little about the power. And then we said that for solving the power issue, we can now go to multi-core parallelisms with more cores. So that's something that we touched. When we are talking about instruction set, it means that there is a set. So it's similar to every language. When you use C language, you know there is, for example, for, if. These keywords, these instructions, these code statements are there, and that's it. You cannot use, for example, in C you write, for example, sit down. In C language, we are writing its own keywords. So the list of instructions of a computer forms instruction set of the computer. And different computers have different instruction sets. It's not the same. But there might be, as we talked, there might be several computers, several processors, which have the same instruction sets. But it doesn't mean that all of the computers have the same instruction set. They have different instruction sets. But the idea and the design of instructions are almost similar. So because designers are doing that, and when they design something and it's good, they will use it for other instruction sets also. So the design is there. And at the beginning of the time, which was around 1960s, where IBM started instruction set, then Intel proposed CPU and instructions. The instructions were very simple instructions, doing add, if, like if, we call it branch in instructions. That's just that, a very limited vocabulary, very limited instruction sets. And at that time, because it was at the beginning of the technology, it was easier to implement those instructions. Then, after a while, we made instructions more complex and more complex, because we wanted to improve the performance. And one of the improvement in the performance was what? Was instruction count. Again, instruction count times CPI times clock cycle. So if you decrease instruction count, it means that you would get a better result, a better performance. So they tried to minimize instruction count. So they started making complex instructions, as you told. You were talking about complex instructions. Okay. But later, in 1980s, when we do complex instructions, it means that the hardware executing that instruction would be more complex. And when the hardware is more complex, it means that there is more delay in the computer, in the processor, when you want to do something, because it's doing more complex operations. And it became less clock frequency. So that's something that we noticed. When we made them complex, then we noticed that the complex gets complicated and the clock cycle will be lowered. In 1980s, the two famous professors that we have talked about them lots, Dr. Hennessy and Dr. Peterson, one of them was doing PhD. I don't remember which one of them was doing PhD, and his PhD, he had this idea, perfect idea. He was saying that usually when we have an instruction set, let's say 100 instructions, usually in 20% of the time, in 80% of the time, it doesn't write, 80% of the time, we are using only 20% of instructions. Yeah? 80% of the time, we are writing programs when they are compiled in the computer. Then we see the instructions which have been compiled there and they are going to be executed. We see that it is only 20% of the instruction set, the whole instruction set, that we try to make it more complex, more powerful. So why should we do that? When only 20% of time, the rest of 80% instructions are used. So why do we do that? Because when you have 100% instructions, you want to execute all of them, then it is harder. But compared to having only 1/5 of those instructions, 20%, the design would be much more simpler. And the simpler design makes faster design. So this idea, which we call it RISC. RISC. What is this, the RISC? Abbreviated for what? Do you know?
Is it like reduced instruction set computer?
Very good. Where did you find it? Did you have in the lectures or you yourself? Yeah.
Book. It was also, I think he mentioned it in the video that you made us watch.
Oh yeah, perfect. Yeah, RISC. Reduced instruction set computing or computers. Reduced instruction set. You know, you see the point? Reduced compared to CISC. Complex instruction set computers or computing. So I told you, at the beginning, the instructions were very simple. Then we went to make them more complex, to do more things than that. And then again, we had the idea that why do we do more complex things? The simpler is faster. So again, we went to idea of RISC. You see here, many modern computers also have simple instruction sets. So it started from simple, then complex, then again simple. Nowadays, the modern computers also have simpler instructions. Why? Because it is simpler to design, and then when it is simpler to design, it is less complex, and then it is faster. It will be faster. So the instructions are almost simple. We will go now to a modern computer. Yes?
So I've heard that modern CISC systems like the x86 are actually RISC underneath and use software to translate in between CISC and RISC instructions.
Perfect.
True?
Yes, because remember I told you Intel has had an idea of batch compatibility. Yes, he wanted to have it support of the previous instruction set that they had. So they didn't change the whole instruction set and making it RISC. So what did they do? They were very smart, Intel engineers. They kept the instruction as complex as it was, and compiler knew how to compile the high-level code to those instructions, those complex instructions, and inside the processor, they somehow translate these instructions to simpler one, RISC one. Why? Why do we go to RISC again? Because, yeah.
I heard it's it's essentially a software-based tool because they can actually issue updates.
Yes.
This translation layer to make
exactly. So whatever we want to do it in hardware, we have to do it in hardware. We do in hardware. If it is possible to do it in compiler, to software part, then that will be easier. Because in software you write a compiler and then it compiles your code and then your code goes to CPU and the CPU will do it very fast. So whatever we can, we do in compiler. But if something we cannot, then it goes to hardware. You are right. At the beginning, Intel designed the hardware to translate those instructions to micro operations. They call it micro operations. Then later, they tried to make a better compiler. Why do we put it in the hardware? In the compiler, we make the better compiler. Yes, exactly. Now we are going to work on MIPS instruction sets. So as I mentioned, x86 is a machine. It has its own instruction set. We go to MIPS instruction set, which with the idea of RISC. And the MIPS is something that Hennessy and Peterson invented, and then after that, a commercialized company named MIPS has been generated. Okay. Stanford MIPS, commercialized by MIPS Technology. You can see at the website, go to www.mips.com. You see how the company is doing. And it is almost similar or based of many modern computers and ISA today. And you could look at the MIPS reference data in your book, and also Appendix E and B. Similar ISAs have a large share of embedded core markets. For example, ARM microcontroller, ARM processor. ARM processor has a huge share of embedded computing now. I think most of our mobiles using ARM processor, ARM core, okay? The instruction set of ARM is not exactly as MIPS, but they are very similar. Similar ISIs have been set. Other also computers, like for example, x86 is different instruction sets, but they're similar in idea and in concepts, which we will touch. So let's start to see some instructions. You remember that in one slide I showed you, you write your code in, for example, a high-level language code, for example, C, Python, Java, in a high-level language code. Then it comes to an assembly language, which is text-based, we can read it, and then it goes to a binary translation, which we call it machine code. And this machine code is the one which will be executed by the processor. Okay? Now I am showing you some of the assembly codes that it will be translated to that. And from here to here, it's just an interpretation. It's the same almost, but just interpretation. We will, in our course, we will talk about this translation. We don't talk about this translation. It is the course of compilers. The software engineer students, they should have a course on compilers, and they will talk about compiling high-level language to low-level language. But in our course, we will talk about this, how from assembly we go to machine code, and how the machine executes the instructions. So let's see an example, a very basic, typical example. It's not exactly as it is in MIPS, but it will give you the idea. Add and subtract. In MIPS-like machines, add and subtract have three operands. Two of them are added, and the result will be put in the destination. So the format would be like that. Add A, comma, B, comma, C. What does it mean? It means that B and C are summed up, and the results will go to A. Add A, virgule, comma, B, comma, C. In C, we write like that. In C, we write C gets A plus B. This is what we write in C. But in assembly, add A, comma, B, comma, C, or virgule, B, virgule C. Okay? All of the arithmetic of operations that we will see in instruction set, they're like the same thing. Two sources, one destination. Two sources will be operated on them, and then the result will be stored in the destination. One of the design principles that we have talked in our course was simplicity. If you make it simple, then it will make it regular, and when it is regular, the design would be simpler and the design would be better, and you get a better design, better architecture, faster architecture. So the first rule is simplicity. This is the idea of RISC, reduce instruction set computing. Simple. Make instructions as much as simple possible. Regularity makes implementation simpler. Simplicity enables higher performance because it is a better clock cycle there. Okay, let's look at a C code. In C, we write something like that. F gets G plus A, H minus I plus J. So we have to add G plus G and A, H first. We have to add I and J, and then we subtract these two. So how this code will be translated in assembly? In assembly, we have three operands. Here we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 operands, 5 variables. In C, we call them variables. So what do we do? We do them 2 by 2. For example, we put, let's say G and H are two things that we can add them together. So we add them together and we put them in a temporary place. We call it T0. So T0 gets the sum of G and H. Then we have another temporary place, T1, and we add I and J. Okay, so now we have this part and this part. Now we have to subtract this. So sub T0 and T1, and the result goes to F. So the one statement that we had in C translated to 3 different instructions in assembly. Okay, any questions? In our machine, we are going to see operands at A, B, C. These operands, we use registers for them. We have some storage place in processor that they store like variables in C, and then we can operate on them, add, subtract, and, or, these things. We will work on the registers. So registers are the one that will be used in arithmetic operations. For every processor that you are going to study, it's good to start with registers. How many registers does it have? What is the name of the registers of that CPU? If you learn about MIPS, then if you go to x86 and we want to learn that instructions, that would be very easy. You have the ideas here, they're the same there. If you go to ARM, it's almost similar. You learn very fast. So the ideas are the same. So the first thing that we are going to talk is registers. MIPS has 32 registers. So we have 32 registers. And each register has 32 bits wide. Okay, so MIPS has 32 by 32-bit registers. They will be used in all of the operations of the processors when it wants to do something. We call them, the registers are from 0 to 31, but we will give you the name of those registers. Since the operations in the MIPS will be 32-bit, you add 2 32-bit, you subtract 2 32-bit, then we call them word. The word in MIPS is 32 bits. How many bits is a byte? How many?
8.
8. A byte is 8 bits. A word is 32 bits in MIPS. So when we want to say about 16 bits, what do we call? We call half word. Byte, half word, and word. 8-bit, 16-bit, and 32-bit. In the names of them in MIPS machine are these. $T0 to $T9. 10 registers here, 10 registers. We will use them usually for temporary values. Then we have $S0 to $S7. 8 registers which will be used for storing variables when you want to have some variables. The principle number 2, smaller is faster. When you only have 32 registers, then the design would be better, the design would be simpler, and again, when the design is simpler, the machine is faster. The same idea of that we repeat. Simpler, faster. First design rule was regularity. The second one is smaller. When you have a small set of registers, like 32 registers, then it would be better design. Compare this to main memory. Main memory has lots of, for example, now you have around 32 gigabytes address space in your machine. The main memory has 32 gigabytes. Compare 32 gigabytes to 32 registers. It is how many times? 1 billion times. 32 gigabyte to 32 words. So it's almost billion divided by 8 times. Okay. Let's now go to the exact terminology, exact vocabulary of MIPS. At the first example, I just used a hypothetical example. This one we had seen before. When you want to make it in MIPS, assume, now for the time being, assume that this one is stored in S0, this one S1, S2, S3, S4, dollar S1, S2, S3. Now our code will be something like that. We add S1 and S2, which are G and H, and we store it in T0. I told you, $sign T0 will be used for temporary values, but S registers will be used for storing variables in code. Then we use S3 and S4, we add them. S3 and S4, we add them and it goes to T1. Then we subtract these two and make it in S0, T0 and T1 subtracted, and the result go to S0. So this will be the assembly code in MIPS for that statement in C. Now you have seen arithmetic, a simple arithmetic command, instruction, which was add and subtract. So what if we want to do something on memory? So everything is not in the registers. When you start your computer, the computer is blank. Then we have something in the hard disk. Operating system will bring something from hard disk to memory. And from memory, you should bring it to the registers. And then you work on that. So again, I emphasize on this idea. When you want to work on something in memory, please pay attention. You bring it to registers and then work on them. This is again is an idea of RISC. In CISC computers, you could work on memory directly. You say, for example, go and add 5 to the memory location 67. It is valid in a CISC machine, but it is not in a RISC machine. In a RISC machine, you should first bring the memory location 67 into the registers, and then you add whatever you want to that register. Got the idea? Reduced instruction set. We don't want to use very complex instructions. So if we can make one instruction which was add 60 plus the memory location of 89 to two instructions. One, bring the memory location 69 to the register and then add it to the add. So why don't we do that? Because that instruction is not used too many times. It is less frequent. So we put more emphasis on the more frequent instructions. Make the common case fast. You remember the ideas? 7 great ideas. Make the common case fast. When there is 20% of instructions which will be used more and more frequent, make them fast. Don't disregard the other 80% of instructions. So main memory is used for storing data. Of course, we need main memory. We need lots of storage, arrays, structures, dynamic data. But when we want to apply arithmetic operations on them, we have to bring them into the registers, into this processor. Back, yes.
So when you mentioned making the common case fast, is that attribute associated with bringing the memory into the register?
Yes. Why? Because the common case is the operations that we can see there, and working with memory locations is not the common case. You bring something in the in the computer, and then you do a lot in the computer. So it's almost, you can say that 20% of times you need memory locations, and 80% you need operations inside the computer. So why don't we make this fast and don't think about that? Instead of that, we make them in two instructions. First instruction to bring it to the computer, and then work on that. So here you see, to apply arithmetic operations on memory elements, load values from memory into registers. So you heard the word load. Load means to bring something from the main memory to the registers. And then after you have done with it, you do a lot of operations, arithmetic operations, logic operations, so many things. Then when you are done and the result is ready, the result should be stored back to the main memory. And then you use store results to memory. Load and store. Now you can understand why we call these machines, RISC machines, as load store machines. Load store machines means those processors who have only load and store instructions to work with memory. There is no other instructions, only load and store. But in CISC computer, for example, you had an instruction to go and add something to the memory location of something. We don't have this in RISC machine. In MIPS, we don't have. We only have load and store. We load something from the memory to the registers, we work on that, and then we store it back to memory if necessary. When we are talking about memory, I don't know if you have something in previous courses, maybe in ITI 1100, yeah? Did you talk about memory? Something like that, I don't know. You have the idea, you know the idea of address, content of a memory, yeah? Give me a feedback, yes? A little. Okay, we will talk about it a little. When we are talking about memory, it means that let's draw it as an like of several several cells. These are cells of memory. For example, this memory that I've drawn here, it has, let's say, 1 mega cells, 1 mega, and then each cell has 8 bits data. So this memory is 1 mega times 8 bits memory. 1 meg times 8 bits. So if you look at this memory, 1 meg times 8 bit, could anybody say how many address bits we need to address this memory? How many address bits? Let's give you a simple example and then go to the higher. Let's assume that we have a memory of 4 cells. How many address does it need? You want an address to make every every location of that. How many? 4 locations.
Oh, I was going to say 4 megabits, but...
No, this just start from this and then we go that. 4, only 4. 1, 2, 3, 4. 4 locations. If we have a memory of 4 locations, how many address do we need?
4.
How many? 4. We can make it better. 4, if you say 4, then how many address bits I am saying? How many bits? With how many bits you can count to 4? 2. With 2 bits you count 0, 1, 2, 3. 0, 1, 2, 3. So you need 2 bits to address the memory locations for a 4-cell memory. Yes?
So for the 8-bit, we need 3?
8 cells, not 8 bits. 8-cell memory. If you have an 8-cell memory, you need 3 bits. This cell would be 0, 0, 0. The next one would be 0, 0, 1. And the last one would be 1, 1, 1. Okay? Yeah? If it is 16 locations, then you need 4. If it is 1 meg, how many do you need? 1 meg. You should be very fast with binary and this. Kilo. 1 kilo. If it is 1 kilo, how many bits do you need? Kilo is 1024. 2 to the, which power would be 1024? 10. Who said? You said 10. Okay. If 2 to the 10 is 1 kilo, then what would be 1 meg? 1 meg is 1000 kilo by kilo. 20. Very good. So this memory needs 20 address bits to show every location of the memory. So this is one thing. And then the other thing is the content of each cell, which in this example I told you it is an 8-bit memory. So how many data bits does this memory have? Data. We want to put data inside and outside of the memory. How many bits do we have? Do we need? 8 bits. Yes, 8 bits. So I can draw this memory with 20 address bits starting from A0 to A19 with 8 data bits. Could you tell me at the back? You. Raise your hand. No, at the back. You. Yes, okay. Could you tell me why I put this as a unidirection and this as the bidirection? Could you have any guess? Could you guess? That one is address bus. This one is data bus.
Can you repeat?
Yes.
The other one is what? I didn't hear the first thing you said.
What?
I didn't hear the answer, sorry.
I didn't answer. I just put the question. Yes, please.
The first one is the address bus, second one is data bus.
Yes, this one is address bus, this one is data bus. And for address bus, I made it as a one direction. For data bus, I put it as bidirection. Why? My question is why? Yes?
Because for the address bus, you're assigning values
Okay.
to something.
To the memory.
To the memory. But with the data bus, it goes both ways.
Why?
The user, because it's not temporary.
Yeah, but why do we need it 2 ways?
Because the computer and you both need to be able to read it.
Read it 1 way and write it. In memory, you read and write. Or in our language, load and store. You do either load, either store. So you need data going inside memory or coming out of the memory. So the data bus is bidirectional. But address bus, you provide address to the memory. You say, for example, memory, I want your content of location 68. So you provide 68 to the memory, and then memory goes to location 68 and finds out, for example, inside the location 68, it has already a value of 17. And then it will give you 17 at its database. This is the read operation, when you want to read from memory. If you want to write in memory, you say to the memory, memory, I want to write, for example, a value of, let's say, 23 in location 125. So you provide 125 to the memory as address, and then you provide 23 as the data you provide. This time you provide. At the read time, you get from the memory. You provide 23 to the memory, and then it will get 23 and goes to the location 125 and stores that in, for example, the location of 205. The value of 23 will be stored in memory. Okay? Yes, please.
So would these commands in the CPU be issued to the memory controller?
Exactly.
Or because I know in DRAM, for example, they have like a different organization structure. They have like banks.
But the idea is the same. Every DRAM, every memory has address bus and data bus. But if you want to talk with the memory, for example, DRAM has a specific interface and so on. So, but these are the same. When you buy a DRAM and you go and buy a DRAM, let's say 1 gig DRAM. When you say we buy 1 gig DRAM, it means that it has 1 gig cells, and if it is 1 gigabyte DRAM, and each cell has 8 bits. So 1 gig DRAM means 30 address bits. 2 to the 30 is 1 gig. 2 to the 10 is kilo. 2 to the 20 is meg. 2 to the 30 is gig. 1 gig of memory, okay? So let's continue. Okay. Now I told you about memory. In MIPS architecture, we know that memory is byte addressable. Byte addressable. What does it mean? Okay. What does it mean? I've talked about memory and said that each memory contains data. In MIPS, MIPS is a 32-bit processor. It means that the registers are 32 bits, I told you, 32-bit wide. So it means that when it wants to talk with memory, it can talk with 32 bits. So each memory location could be 32 bits, which can be talked with the processor. But even if this is the ability of MIPS to talk with the memory with as 32 bits wide, but all of the designers of processors have agreed that we have to maintain byte addressability. Why? It means that when you have 32-bit locations, then each location has 4 bytes. Is that right? 32-bit is 4 8-bits, 4 bytes. Okay. When we are saying that we have byte addressability, means that this byte is address 0. The next one would be address 1. The next one would be address 2. And the next one would be address 3. These 4 combined together make a word, which MIPS could communicate with memory in words. But again, I say, they have to maintain byte addressability. It means that if MIPS wanted to read 1 byte from memory location 2 should be able to. Memory location 2 is this. So MIPS should be able to read 1 byte from memory location 2. But remember again, the memory would be designed in 32 bits because MIPS is 32 bits. It can read 32 bits from the memory. The data bus of the memory and the MIPS would be 32 bits. But at the same time, they need to maintain byte addressability. And it will give them a burden on the designers to keep the byte addressable. But it is useful because sometimes you write a program that needs bytes. You don't need 32 bits a word, just every 4 bytes. No, you just need 1 byte. So you could have 1 byte. We will talk about byte addressability later. If you have any question, you could say no, but we will talk about it more later. Memory is byte addressable. Each address identifies a byte, 8 bits, a byte. Okay, now that we talked about byte addressability and said that addresses are bytes, again we go back to our memory. Our memory, as I told you, each cell has 32 bits, but with each cell has 4 addresses for that because it is byte addressable. So the cell number 0, 1, 2, 3 form row 1 of the memory. Row 2 of the memory would be cell number 4, 5, 6, 7. Row 3 of the memory would be cells number 8, 9, 10, 11. When we are talking about alignment, here you see words are aligned in memory. The idea is that when you want to access the memory, you should do with alignment dictation. What does it mean? It means since we are going to use the memory as 32 bits for MIPS, because MIPS is 32 bits, if we cannot use 32-bit memory data, why did we go to 32-bit bus? We could stick with 8-bit bus, as for example, 8085 processor in 1982. In 1982, 8085 processor had 8 bits of data. The registers were 8 bits. But MIPS is 32 bits. We want to be able to get 32 bits from the memory. So if you want to get 32 bits from the memory, then the address should be 0, 4, 8, 12, 16, 20, and so on. Why? When you say, okay, I want memory, I want 1 word from you at address 4, then it means that the MIPS needs this row. Okay? You cannot, when it is only aligned, it means that you cannot say memory, give me 1 word from address 2. Address 2 is here. 1 word from address 2 means, hypothetically, means address 2, 3, 4, 5. But 2, 3 are here, 4, 5 in another row. It is non-aligned access. In MIPS, non-aligned access is prohibited. Words are aligned in memory. You can access the words in aligned address. What does it mean? Aligned address means addresses which the mode to the 4 is 0. It are divisible to 4. 0, 4, 8, 16, 20, and so on. So the memory is aligned. Some processors, they allow non-aligned access. For example, x86. x86 allows non-aligned, but makes it more complex. When you want to access a word from address 2, x86 thinks that, okay, it is address 2. So it means that I have to bring memory locations 2, 3, 4, and 5. And then it finds out that, okay, 2, 3 in row 0, and 4 and 5 are in row 1. So I make it 2 memory access, 1 to the row 0, and from the row 0, I just use the half high of the memory of the data, which are location 2 and 3, and then I generate another access to memory to row number 1, and I get 4 and 5 from there, and then I put them together, 2, 3, 4, 5. You see how complex it will be, an execution of a non-aligned access. Yes.
This is why like modern x86 system benefits so much from faster memory speeds.
But they still support non-aligned.
Right. I know, but is this why like a lot of modern systems you see like essentially linear performance with memory speed, like higher memory speed and
No, that won't be the reason for that. Why? Why do you say that? Aligned access, you mean? No,
because it allows non-aligned access. Is that why
No.
you get more benefits from higher memory speed?
No, I don't think so. It is vice versa. It's when you have non-aligned access, it makes it slower. But they do something to make it fast. But for sure, memory access of x86 is slower than memory access of MIPS. Why? Because they didn't allow it. It doesn't mean that, okay, they did allow it and they did something there. No, they didn't allow it. If you write in your code, go and bring one word, load one word from address 2, it will give you a problem, an error. It says non-aligned access is prohibited. The compiler or the assembler doesn't allow that. You cannot load a word from address 3, address 2, address 1. You can from address 0, address 4, address 8, and so on. Since I told you this, let me say this one also. If you want to load 1 byte, then that would be okay. You can load 1 byte from address 0, address 1, address 2, address 3. It's okay. This is 1 byte. It is non-aligned because you only need 1 byte. You could load a byte from any address location. And we maintained byte addressability. So you can load any address, a byte. And if you want to load half word, could you load a half word from address 2? Address 2. This one.
You have to load the whole word first.
Yes, but could you do the half word from address 2?
You mean just 2 and 3?
Just 2 and 3, exactly.
No.
Yeah, we can because it is aligned, because it is in one row. So loading half word from address 2 is aligned. It's okay in one row. But loading half word from address 3, no, because one is here, the other one is here. 4 is at the other row. It's not aligned. Okay? So aligned words would be 0, 4, 8, 16. Aligned bytes would be everywhere. Aligned half words would be 0, 2, 4, 6, 8, 10, and so on. Okay? Address must be a multiple of 4 for accessing words. The other thing that we should discuss first now is big endian or little endian. Have you heard about that? Little endian, big endian? No? You haven't seen Gulliver cartoon? No? Gulliver. Lilliput.
When did it come out?
You didn't? See, Gulliver cartoon. Gulliver is going to a place, Lilliput, that the inhabitants are very small.
Gulliver's Travels.
Huh?
Gulliver's Travels.
Gulliver's Travel. You have seen that?
Yeah.
Okay. And the place is Lilliput. Gulliver traveled to Lilliput. Did you see or just you saw?
The one with Jack Black.
Okay. In the Lilliput, one of the Gulliver's finding there that they were quarreling about how to break an egg. Some of them was breaking the egg from the bigger side, some of them from the lower side. I guess you also do the same. Some of you crack the egg from the bigger side, some of you crack the egg from the lower side. Those were called big endian. The other ones were called little endian. In computer industry, they got the word from there, and we have two kind of computer architectures, big endian and little endian. What does it mean? Okay, we talked about byte addressability, and I've told you that if you have a memory and the memory is aligned in 4 bytes, so we have address 0, 1, 2, 3 arrow, 4, 5, 6, 7 arrow, and so on. Okay. Now I want to store a value in location 0. I told you that you could load or store word in aligned addresses. Let's say that we want to store a value of 32 bits. 32 bits. Let me put, for example, do you know hexadecimal? I guess in ITI you had. So a 32-bit hexadecimal look like something like that. For example, 8, 2, 4, 7, 9, D, and 1, 0. This is a 32-bit number in hexadecimal. Okay? Everybody okay with that? Okay. So when we want to store this number, this is a number. This is a 30-bit number. When we want to store this number in memory location 4, what do we do? Memory location 4 is 1 byte. And I told you that location 4, 5, 6, 7 form a word for you. So you have to store this number into these 4 locations. How do you store it? You suggest. Yes?
I'm not sure.
There are 4 numbers, 4 bytes with 4 addresses. What do you suggest? Where do I put 10?
In 4.
In 4. When do I put 9D?
Just consecutively.
Okay, perfect. 9D, 47, and 8. Okay. This is called little endian. It means that you put the lower byte to the lower address. So it is little endian. MIPS is not like that. How does MIPS store? So you tell us again. What do you think? 10 is stored in where? Oh, the same percent. Oh, you tell us. Okay. Yeah. You want? 10 goes to
7.
Perfect. Goes to 7. 9D goes to 6. 47 goes to 5, and 82 goes to number 4. So this is big endian. Big endian. MIPS is big endian. So why it is big endian? I don't know. x86 is little endian. If you go to x86, they store like that. If you go to MIPS, they store like that. You can Google about little endian and big endian to see why they do this, why they do that. I don't know. It's like I don't know. It's like, I guess, Real Madrid and Barcelona. If you like Real Madrid, when I ask you why Real Madrid, not Barcelona, you like it. I cannot do anything. and who they like Barcelona, they like Barcelona. We cannot do anything. Could we? Could you ever try to convince somebody that likes Barcelona to like Real Madrid? You cannot. It's something there. And this is the same. Okay, thank you very much. I tried to record the remaining slides of the previous lectures for you so you could watch it in your own time. Thank you. Have a good day.
We don't have class for DGD on Monday, right?
Oh, yeah. Monday is a holiday, yeah?
I think so, yeah.
Ah, yeah. So
Okay, just one.
no class, no DGD. Too bad. Okay. Or too good.